As promised, today we'll talk about molecular orbital theory, which is a much more robust way of treating molecular electronics that leads to better predictive value across a range of properties. One of these properties is magnetic susceptibility. When we weigh a sample in a magnetic field, which we can do with a Guy balance, it may be attracted to that magnetic field, which changes its weight. This is called paramagnetism, and it occurs when there are unpaired electrons in a molecule, which is often the case when the highest energy electrons are in degenerate orbitals. We end up with two electrons that are both pointing in the same direction, but don't have electrons pointing in the opposite direction that they're paired with. The magnetic properties are only displayed in this case of paramagnetism in the presence of a magnetic field. A sample might also be weakly repelled from the magnetic field, diamagnetism, that occurs when all electrons are paired. Diamagnetism occurs frequently with both degenerate or non-degenerate orbitals. Paramagnetism and diamagnetism are distinct from the more familiar ferromagnetism that gives rise to permanent magnets. These magnetic properties are only felt when we have other magnets as well. As we talked about last section, both valence bond theory and molecular orbital theory start with the basic understanding that electrons and atomic orbitals are both particles and waves. And since electrons have wave properties, they can overlap constructively and destructively. And again, the more we overlap in phase constructively, we end up with bonds. On the left, constructive interference leads to a bigger wave indicating a bond, and again on the right, destructive interference leads to the destruction of both waves, the opposite of a bond or an antibond. In molecular orbital theory, those antibonds become much more important. In many ways, molecular orbital theory looks similar to valence bond theory. In both, we make linear combinations of orbitals, we add them together to create the same number of new orbitals. In molecular orbital theory, however, every atom has the potential to participate in every linear combination, even if it's farther away, and the atomic orbitals within a single molecule don't form hybrid orbitals. We get these molecular orbitals by combining the orbitals in phase or out of phase, which means that in molecular orbital theory, unlike in valence bond theory, we account for molecular orbitals that are antibonding, that repel the nuclei instead of holding them together. We indicate these types of orbitals with a Greek letter to indicate their symmetry, just like with valence bond theory, sigma, pi, and even delta. But then also we have a star to indicate the antibonding characteristic, which we can see on the right as the pi star orbital. Again, we don't use hybrid orbitals in molecular orbital theory, but our p orbitals can overlap just like sp, sp2, or sp3 hybridized orbitals overlapped to form similar sigma bonding interactions. But now in molecular orbital theory, they can also overlap out of phase to give antibonding orbitals. So we see the in-phase overlap of p orbitals giving a sigma px orbital, but we can also see the out-of-phase interaction giving a sigma star px orbital. And of course, we can have pi bonding orbitals just like before, but we can also have pi star orbitals that have a node between the nuclei and repel bonding. Only bonds of the same symmetry can interact, just like in valence bond theory. For example, on the left, 3px and 3px both have sigma symmetry along the x-axis and can form sigma bonds. The 3px and 3py orbitals, shown in B, have different symmetry along the x-axis. 3px has sigma symmetry, but 3py has pi symmetry. There is no such bond as a half sigma, half pi. The top half would subtract and the bottom half would add, and they altogether would just not interact. The 3py orbitals can still interact with each other, of course. They have pi symmetry in the x-axis and would make a pi bond. So molecular orbitals are created by combining orbitals of the same symmetry. They really only combine if they're similar in energy. If they're too far apart, they don't interact. We can see this fairly clearly in simple homodiatomic, which means same two atom molecules. Identical orbitals from each atom will interact with each other, but we don't see a lot of interaction between orbitals that are different between each atom. When we actually do these calculations, we'll use computational packages that can solve the Schrodinger's equations for the entire molecule using a set of assumptions. Right now, we're just trying to see qualitatively what type of molecular orbitals emerge in simple cases. This molecular orbital diagram shows a molecule of diberyllium, positive, which has a total of 3 electrons. The two s orbitals combine with each other to make a bonding sigma orbital, which you can see on the very bottom, the sigma 2s, and an antibonding sigma orbital, which we can see highlighted above it with a sigma star 2s. The px orbitals also combine to make sigma orbitals. The overlap is significant, so the bonding stability is greater, which is why the sigma 2px is low, but the destabilizing in the sigma star 2px is also greater. The pi overlap is less than the sigma overlap, so the pi stabilization and destabilization are less, which is why the pi molecular orbitals formed from the 2py and 2pz orbitals are within the sigma orbitals. All these orbitals exist whether or not they are occupied. The ground state fills in the same way atomic orbitals do. 2 electrons per orbital, lowest energy first. So diberyllium positive has a pair of electrons that are in the lowest energy bonding orbital and just 1 electron in the next energy antibonding orbital. If we can draw a molecular orbital for a molecule or an ion, we can use its electron filling to give a more accurate representation of its stability. For example, the hydrogen molecule only has 2 electrons in the sigma 1s orbital, a bonding orbital. Since one bonding orbital is full, we say that the bonding orbital of hydrogen, H2, is 1. The hydrogen molecule has a single bond. We can look at dihelium with the same approach. Because helium has more electrons, both the sigma and sigma star molecular orbitals are full. The full sigma adds 1 to the bond order. The full sigma star subtracts 1 from the bond orbital. So the net bond order is 0 and dihelium doesn't exist. With helium, it's kind of trivial. We know that helium doesn't bond to anything. But it lays an important foundation for understanding how we think about the creation and destruction of bonds in more complex molecules. Adding electrons into a bonding orbital creates a bond. Adding electrons into an antibonding orbital negates the corresponding bonding orbital and destroys that bond. So here's an example of how this comes into play in organic chemistry. If we want to destroy a pi bond to make a new bond, it can happen in 2 ways. One way is to have some sort of source of electrons, maybe a sigma bond with high energy electrons, maybe a pair of non-bonding electrons. Those electrons can add into a pi star orbital as shown, with the arrow going from the electrons to that empty pi star orbital. When this occurs, there's a new bond formed where there was appropriate overlap with the pi star bond, and the pi bond that we had before is negated. This not only explains why we see a lot of reactivity where we see it in organic chemistry, it also explains why we see products occur in the geometries that we observe. So this ends up being a very powerful way of looking at many of our reactions. We can also destroy a pi bond by using its electrons to do something else. This happens fairly frequently, since pi bonds are often some of the higher energy electrons in a molecule. Here a pi bond is sending its electrons into a sigma star orbital on another molecule. Since the pi electrons won't be in a pi bond anymore, the pi bond would be destroyed. A new bond will form where the antibonding orbital was on the other molecule, and the corresponding sigma bond on the other molecule would then be destroyed. As you add electrons into an antibonding orbital, it destroys the corresponding bonding orbital. We can do these molecular orbital diagrams for any molecule. In this chapter, we're just talking about how the simple molecular orbitals work, but we'll get into the much more powerful descriptions, particularly in organic chemistry. Shown, you can see the MO diagrams for dilithium on the left, which incidentally is stable in many cases there are any Star Trek fans, all the way to neon, but without showing the filling or the 1s sigma and sigma star molecular orbitals, because those orbitals are full in every one of these cases. Before we start filling in the electron occupancy, I want to note something curious that's apparent when we look at all the molecular orbitals aligned. Starting on the right and back through oxygen, the molecular orbital diagrams look as we'd expect. They occur in the order, so reading from the bottom label on the right, sigma 2s, sigma star 2s, sigma 2px, pi 2py and pi 2pz, then above that pi star 2py and pi star 2pz, and 2px all the way on top. What's curious is that before nitrogen, the sigma 2px orbital is actually higher than the pi 2p orbitals. You can see that switch to the other side, which would suggest that it's less stabilizing. That's because the 2s sigma and 2p sigma type orbitals are similar enough in energy and have identical symmetry, which allows them to mix. This occurs most when they are most similar, which happens before the nuclear charge gets high. It happens most significantly early in the second period. So we know that orbitals can mix if they have similar energy and identical symmetry, but we can also see that this is advantageous for those early second period elements. Let's say that this diagram shows the mixing for C2. If we start out with the unmixed molecular orbitals on the left, we can see that carbon's 4 valence electrons apiece would fill the lowest 3 molecular orbitals and then half fill the pi orbitals as shown. Compare this to what happens when those same electrons combine after mixing. Even though the sigma p orbital increases energy, as does the sigma p star orbital, the sigma s orbitals both decrease by the same amount of energy, because both sigma s orbitals, the sigma and sigma star that decrease in energy, are occupied, but only one of the sigma p orbitals that increases in energy are occupied. The net result is a much more stable configuration. Another way of stating that is overall the arrows are lower on the right than they are on the left. Now that we have that mixing weirdness out of the way, we can talk about orbital filling and bond order for each of these molecules. Starting from the left, we have dilithium. Each lithium brings 1 electron, so we have exactly 1 pair of electrons in the sigma 2s orbital. Since this is a bonding orbital, we say that dilithium is stable with a bond order of 1. A quick side note about stability. All of these calculations are for molecules existing in the gas phase, where they don't really interact with anything else. It's in this context that dilithium is stable. Lithium would much rather interact with a host of other things, so this is only observable in the gas phase, but not in other phases where lithium would actually come into contact with anything other than itself. Stable is always relative. Moving on to diberyllium, each beryllium brings 2 electrons, which means that the sigma 2s and sigma star 2s orbitals are occupied. 1 bond and 1 antibond means that beryllium, or diberyllium, has no net bonding interaction and therefore has a bond order of 0 and is unstable. Unstable, unlike stable, can be in an absolute sense. It just doesn't form ever. Next to the right, we have boron. With boron, we can get 2 more electrons. Since the next highest orbitals are degenerate, we get 1 electron each. Each contribute half of a bond for a total of 1 bond between the two. The sigma 2s orbital cancels out with the sigma 2 star, sigma star 2s orbital, and boron has a net bond order of 1, or diboron has a net bond order of 1. At this point, we've done 3 examples. See if you can fill in the electrons for dicarbon through dineon and use those to predict the bond order of each. Carbon, like we saw on the last slide, has 8 total electrons, filling 3 bonding orbitals and 1 antibonding orbital. So carbon has a bond order of 2. Nitrogen fills in an additional bonding orbital full, giving it a bond order of 3. Note that nitrogen is normally a diatomic molecule, and its Lewis structure has a triple bond. These descriptions match. Oxygen puts 1 electron into each of the degenerate pi star orbitals, which together give an antibond. Oxygen has just as many bonding orbitals as nitrogen, but also has antibonding character that give it a net bond order of 2. Again, this net bond order of 2 matches the Lewis structure description we get for oxygen, but more accurately describes its electronic behavior. Likewise, fluorine has the same 4 bonding orbitals, but now has 3 antibonding orbitals full, giving a net bond order of 1. And neon has 4 bonding orbitals and 4 antibonding orbitals full, giving a net bond order of 0. Neon is not stable as dineon. Now that we've shown how we think about how molecular orbital diagrams are constructed, how we use them to give bond order, and even hinted about how we'll use them to talk about reactivity, we can return to our initial premise, why oxygen is magnetic. As we indicated before, Even though we show oxygen with 2 bonds, the complete picture has both bonds and antibonds. Oxygen's pi antibonding orbitals are each half occupied, giving us 2 unpaired electrons that are matched in spin. This makes oxygen paramagnetic. Incidentally, this also makes oxygen somewhat more reactive than you might expect, which is what allows you to do things like your electron transport chain.